Welcome back, nerds. We're going to go ahead and finish up Unit 2.14 today. Logarithmic function, context, and data modeling. See? I love logs. So today we're going to be talking about regression. So very calculator heavy today. And since we're talking regression, we also need to remember what it means for something to be a residual. And a residual value is how far from the true value your model was. And it's always going to be true value y minus modeled value y hat. So that's old material. We'll do it in the notes, but I just wanted to remind you how that works. Okay? So we jump right out of the gates talking about logarithmic regression. Go ahead and go into stat edit. You'll see that I have some crapola in my list, so I'm just going to clear that out. Remember, highlight L, whatever, hit clear, enter. Okay? So there we go. We're going to enter the numbers 2 through 7 as x's. And then your y values. There they are. The calculator only does one kind of logarithmic regression. Natural logarithmic regression. That's the only one that it does. Cool? So go stat calc and scroll down to ln reg. There it is. Natural log regression. Hit enter. Make sure x is L1, y is L2. And let's see if we need to store this thing. Am I going to have to plug anything into it? I'm going to have to plug in x equals 10. So you might as well store it just so you can figure out what f of x is when x is 10. Reminding you how you store something. Press vars, y vars, function y1. There it is. And then hit calculate. Boop. And there we are. Notice the order that it gives it to you. It actually gives you the vertical shift first, then the vertical dilation. Also notice there are no transformations on the x. So the calculator cannot shift or dilate or reflect horizontally for this regression. Okay? It's always going to use the y-axis as its vertical asymptote. Always. All right? Okay. All right, it says to write down the equation. We got it right there. F of x equals negative 2.646. B is positive, so plus 4.654 natural log of x. There. The next question says, use that function, this one, to predict our y value when x is 10. So that literally means figure out what you get when you plug in 10. We have two options. We could either graph it and do second trace value, or we could do my new personal favorite, and that's go directly to the table. But I really cheese the table because I do this second table set, and I tell it to start at the number I'm looking for. And then I do second table. There we go. So it's about 8.07, what does it say, round to the nearest tenth. So about 8.1. Remember, if you're not told how to round, 3 decimals for AP. Okay? Great. This is a y hat. It's a modeled, predicted y value. Now, we can't use these big x's for residuals because we don't have any x's that large. We can only calculate residuals on points that I know the x and y for. This question says, what is the residual value for 4, 4.5? Okay, 4, 4.5. This 4.5 is actual y values. This thing generates y hats. So maybe do that. Maybe that'll help you remember it. Residual values are always calculated by saying real minus predicted. So the real y value is 4.5. minus, oh, we need to figure out what the predicted value is. So again, I'm just going to go to table set and tell it to start at 4.5. There. 4.354. I'm sorry? Oh, crap. I plugged in the y value, not the x value. I'm sorry. I plugged in the y value, not the x value. Dingle-lingle. There we go. Bless you. Sorry. I don't know why I did that. Anyway, there's the y hat. 3.806. So not even 4. 3.806. There we go. And then we just subtract whatever 4.5 minus 3.806 is, 0.694. There it is. So remember, a positive residual means the actual y value is above the model, which we can see because it's a bigger number. Not too bad, right? I think the hardest part about this is, did you remember how to do residual stuff? That it's always y minus y hat. We're going to do it again with a new table. Let me show you a quick little trick. Stat edit. Clearly we need a new y list, so I'm going to clear that one out. But notice the x list is all the same numbers. It's just missing 1. Check this out. Second, insert. 1. There. I mean, what's it going to save you? Maybe 1-2 seconds. But the point is it's there. Insert's right here above delete. Whew. Typing all this junk is tedious. But we got them. The first question says, what's the log regression? And the second one says, what's the linear regression? And the third one says, which one is better and why? Do you guys remember how we determine which ones are better? How? R or R squared. R or R squared. There we go. Those hard words to say. We're just going to use R. Just because. All right. But let's go ahead and tackle logarithmic regression. And do I need to save these? I need to save one of them, and I don't know which one. So I'll save them both. We'll save the logarithmic as y1. So vars, yvars, function y1. Okay, let's get that written down. And this is time versus speed. .5. I have these backwards. It's speed versus time. Time is the input. Sorry. Speed in terms of time. There we go. Anyway, 1.541. This blue pen is not behaving. B is positive, so plus 2.558. Natural log of 2. 2. Why? What is wrong with my brain today? X. Natural log of X. Or T. I can't. You know what? I hate everything. If only I could edit that part of the video out. Anyway. Speed. When time is an input, there's time. There it is. And my R value was 0.991. Rounded to 3 decimals. What is wrong with this pen? No, I like blue pen. Blue pen's been good to me. I'm not sure what the problem is, though. It's clearly having an issue. Okay. Now a linear model. Let's get the linear model. Speed after a known time is So stat calc linreg, and store this one as y2, vars yvars function y2, because I don't know which one I need to use. It's a lie. I do know because I taught this the second period. But the point is, you wouldn't have known. So here we go. And we've got 0.789x plus 1.5t, t, kill me, t, and r is 0.964. So those are both really good models. But which one's better? The logarithmic is better, and why do we know that one? Because its r value is closer to 1. Yep. So because r is closer to 1, the logarithmic one is better, which means when I go into my y equals menu, I'm just going to clear out the second one, which was linear, because I don't need it. It says figure out when this f of x, which I have s of t, whatever, equals 8. So when does this equal 8? So we set 8 equal to our top model, 1.541 plus 2.558 natural log of time. And we could use, exponentials and inverse operations and all that stuff. Or we could just do second trace intersect. I like second trace intersect because it allows us to review an old concept. Here's what we know. We know that the x value is going to be bigger than 7 because I hadn't gotten to 8 yet. So I don't know, 10 might be enough time. I'm not sure. So because I don't know if 10 is enough, I'm going to go to 20. And also, what was I? He broke my concentration because I looked up at him. Oh, and I want to know when it crosses 8. So I just need to make sure that 8 fits on my window. So I go to my window from 0 to 500. Holy crap, that's going to be later in the lesson. From 0 to, I'll go to 20 because I have no idea if it's enough. And then my minimum, 0, maximum, 10 is fine because I'm trying to capture 8. Now, I could have used the table to check for a decent window if I wanted to, and seen that the answer is between 12 and 13. So I guessed from 0 to 20. And so it managed to land there. But I'm going to hit graph, and there's our logarithm. Here's y equals 8, and we can see the answer by doing second trace intersect, which is 5. Enter, enter, and scroll to take a guess. And we see that our answer is about 12.484 seconds. Minutes, excuse me, minutes. It's in minutes. The question says not to round. Okay, so 12.484 minutes. It says explain the meaning in context. We should probably read the words. The table below represents the speed of a coxed boat, a coxed 4, which is a rowing boat used in the sport of competitive rowing. Okay? These are times. These are the speeds at those times. So clearly, the longer we row, the faster we're going. Now, linear doesn't make any sense in this situation because that would imply that we could increase our speed forever. Now, obviously, you can't. And that's why a logarithmic model is actually pretty decent because it peters out. But even this implies that it goes forever. I would argue that an upside-down exponential function is even better because you're going to approach a speed at which humans just couldn't go any faster. But that's not what the lesson was asking us to do. So, yeah. So, in the context, this tells us that it will take about 12.5 minutes for our boat to reach 8 meters per second. There. Yes, sir.
So, how
Well, you had to have already saved it as the y1. So you go to stat, calc, and when you do the regression, you have to store it here. So you go vars, yvars, function, and then y1. And now it'll be your y1. See? Now if you press y equals, it's there. Did it work that time? Okay, you must have just pressed a key wrong or something. Okay, moving on. Here we have a much larger table of data that we have to plug in. And yeah, my favorite, caffeine. A university study on sleep related to caffeinated drinks is shown in the table below. Participants were given 250 milligrams of caffeine in their bloodstream. The caffeine level was measured at various times. So this is the level of caffeine at times. Now, typically, time would be the input, and then the level of caffeine would be the output. But you see, that's exponential. It's exponential decay, because over time, the amount of caffeine in your bloodstream decays. But since we are trying to find an equation that's logarithmic, we're actually going to be doing the inverse, which means our x's and our y's have switched. So now we're allowing the level of caffeine to be our x's, and the time is the y's. Yes. So it's if you knew the level of caffeine, how much time would that have taken? So yeah, it's just the opposite information. And this is a tedious part of the video while I type numbers in. Actually, no, I'm going to pause it. There, movie magic. The table's full. Okay? We are supposed to find a logarithmic regression for this thing. So stat, calc, linreg, or lnreg, excuse me, and I am going to store it because I can't remember, honestly, if I need that or not later on in the question. So vars, yvars, function, y1. Calculate. There it is. Oh, b is negative this time. Be careful. Don't write plus. Yes, Ashley? What's with the face? Ooh, that means your calculator, which is a Casio, calculates these things differently than ours, and we need to do some Googling or some YouTubing to find out how to do logarithmic regression. Okay? Interesting. We'll see how that Casio does it. So we have, I'll write y equals x. So y equals, we have 40.801 plus, crap, I even said it was minus. Oh my gosh, I'm just so bad at this job. I should quit. 7.214 natural log of x. There we go. Remember, x is the amount of caffeine in our bloodstream, and y is the time it took to get there. Okay? Okay. Part B says find the time it takes for an average person to metabolize 50% of that caffeine. So 50% of that caffeine, if we started with 250, what is 50%? Which is, what is half of that? What? You're retyping. No. Half of 250 is 125. So 125 is an amount of caffeine. So this question, we have an input of 125. So we say y equals 40.801 minus 7.214 natural log of 125. Of course, I'm not going to type that because I already have it saved as y1. Instead, I'm going to go to second table set, and I'm going to tell it to start at 125 to give me that number because I'm too lazy to try to figure out what size graph fits. And what I could see is that's about, I mean, if you round that to 3 decimals, it ends up being 2 decimals. But the question says nearest tenth, and if you do nearest tenth, this 5.9698 rounds up to 6. About 6 hours. Okay. Avery drank an energy drink containing 250 milligrams of caffeine at 9 a.m. How much caffeine will be in his bloodstream 10 hours later? So this is a time, which means this is a y value. So we have a Y value of 10. All right. It's looking like it's it's less than 100. We know that because of the table. All right. But I'm not trying to scroll until I find it. So here's what I'm going to do. I'm going to graph it. I'm going to go to my Y equals, and I'm going to set it equal to 10. What we do know is that it's going to happen in less than 100 hours, which should make a lot of sense. In fact, it's probably not going to take anywhere near that much. I mean, oh wait, no. We're trying to figure out how much caffeine is left 10 hours later. So when time is 10, right? I'm confused. Yes, when time is 10. And time is a Y value. So, I don't know. How much caffeine do you think there is? I mean, we know there's 125 at 6 hours. So, I don't know. I'm going to take my window from 0 to 100 on the amount of caffeine. And hopefully that's enough. Have my scale go by, what, 4s? 5s. 5s, that way there's 20 tick marks. And 0 to... Ooh, 250? Oh, no, something's drastically wrong here. Hey, it looks like there's an answer there. Oh, I was looking for Y equals 10. That's why. Duh. Well, I don't know. I'm just fixing my picture right now. There we go. Y equals 10 needs to be in the middle of my screen. I'll be okay. There it is. Okay, so that's Y equals 10. I need it in the middle. Second trace intersect. Second trace 5. Enter, enter, scroll. Boop. Okay. Now, someone in the crowd said, shouldn't it be 77? But how did he know that? I mean, it's not, but what made him think that? It's on the table. But remember, this is experimental data. So the model is going to be the average time. But we should have known it should be somewhere close to that, right? Okay. So we got that it was at 71.497 milligrams. So when was... How much? Wait, this is time. How much did we have after 10 is the question. Oh my gosh. There we go. Speaking of caffeine, I think I need some. What is wrong with my brains? Anyway, what we got was 71.497 milligrams, but it says round to the nearest milligram. So about 71. Okay. About 71 milligrams. And that took 10 hours. The study found that the majority of participants were able to sleep when their caffeine levels fell below 70. So it's going to take a little bit longer than 10 hours. Find the time to the nearest hour for the body to metabolize the caffeine to reach 70. Now the answer is probably 10, but let's go ahead and figure it out. And we know that it was trying to get to 7, right? D, 7D. So it means all we have to do is plug in 70, and that's going to give us our Y value, which was a time. And again, I don't feel like typing that, so I'm going to go to second table set and ask it to tell me what's up at the number 70. And it says it's going to take 10.153 hours. So if you round that to the nearest whole hour, but the question doesn't say how long. Got to watch these words. It says find the time. What we have to make an assumption here is that we're talking about Avery, because Avery took the medicine at 9, or the medicine took the caffeine at 9. So 10 hours after 9 o'clock in the morning is 7 o'clock in the evening. Avery can sleep at 7 p.m. There we go. Use the regression equation. Find the x-intercept to the nearest tenth. The x-intercept, where it crosses the x-axis. So when you're crossing the x-axis, that means y is at 0. But yes, so when you're crossing the x-axis, we know y is 0. So what we're going to do is we're going to graph it, and we're going to see when this thing crosses the x-axis. Anybody want to take a guess at what the number should be close to? Should be close to 250. Because this means 0 time has gone by. Because remember, y is a caffeine. Isn't it? Y is a time, excuse me. So when 0 time has gone by, I can't know why I keep saying it backwards. When 0 time has gone by, there had better be 250 milligrams-ish caffeine. So for my window, I'm going to go from 0 to, I'm going to take it 300, just in case it's bigger than 250, and have that go by 30s. And my Y minimum, I'll go negative 20 to positive 20, just so I can see a good graph. Give it to me now. Ooh, is it going to make it? Almost didn't make it. That was really close to the edge. So second trace intersect, which is 5. Enter, enter, and then scroll. Yeah, maybe I should have gone bigger than 300. I didn't think it was going to be this big. I really thought it'd be closer to 250. 285.963 milligrams. So explaining the meaning, this is the average amount of caffeine in the bloodstream when the study began. So what does it tell us about our model? It tells us the model's not perfect because we know for a fact that it started at 250.
Oh, yeah, that's clear.
Yeah, so it's off. It's off, but I mean, it's logarithmic.
Yeah.
It's not perfect. It's a regression, and it is what it is. Okay? So that's what it tells us. Ready to move on? Yeah? Next question actually could have been part of yesterday's lesson. It's really easy. The wind speed, S, in miles per hour near the center of a tornado is related to the distance, D, in miles that the tornado travels by this equation. So the speed based on distance is 93 log distance plus 65. Or a tornado whose wind speed was 220 miles per hour, that's a speed, so that goes over here, happened in Nebraska, how far did it travel? So you literally just put 220 there and get D by itself. Now you have two options. You could either do y1 is this and y2 is that, second trace intersect. Or you could just solve for D using inverse operations. And I actually think that going the route of graphing would be too much of a pain in the butt. So let's just go ahead and do the inverse operations. Subtract 65 from both sides. That is 155. Now, I don't know what 155 divided by 93 is, and I don't care. So I'm just going to leave it as a fraction. And how do I make the common log go away? Exponential base 10 on both sides. That'll cancel this one. And that'll get me that the distance is that number. Distance is 10 to the 155 over 93 in miles. You must have typed it wrong. 46.416 miles. Ta-da! I actually don't know why that was part of today's lesson. Because then example 12, we go right back to regression. And I'm not sure. But whatever. Who cares? Remember, the extra credit that I'm leaving you with tomorrow doesn't include the 2.14 stuff. It's everything else, 2.1 to 2.13. And here we go. Mr. Craig gave his students a poster of math properties. They studied the image for 90 seconds. Beginning one day later, a quiz was given each day to test their memory of the poster. The table below represents the average score for each day. So this is how much they remembered after so many days. So after the first day, they remember almost 3/4 of it. After 4 days, they're down to 64%. After 7 days, down to 60%, so on and so forth. It says use a logarithmic regression to model the data. So back to stat edit. There. I could have paused it while I was typing it all in, but I didn't. Looking for a logarithmic regression. So stat, calc, natural log regression. Am I going to need to plug anything in? Predict the average test score after 14 days. So I'm going to have to plug a 14 in, so I'm just going to store it. There it is. Oh, and b is negative, so I got to remember to do minus. And it should make sense why it's negative, because we're remembering less and less each day. Where x is the number of days and y is the score. Ooh. Look at that R value. This is not a good model. Look at R squared. R squared's a train wreck. This is not a good model. What's that? It doesn't ask. I just noticed that it's a bad model. Okay. Well, anyway. Use the model to predict the average test score after 14 days. So I'm going to just go to second table set and enter 14. And the second table. Is something wrong? Is my model wrong? Did I type it in wrong? Oh, I missed a 0. Ain't that about a B? Man, that's if it was a 6.5, that's like my Algebra 2 honors scores. Yeah, they bombed again. Yeah, the average was a 62 this time. At least it wasn't an F. Okay, so my model's all kinds of borked. Let me just scribble that out. And too bad I don't have any video editing software. B is still negative, though. Y equals 76.07 minus 7.882 natural log of x. And then, anyway, I don't know. I didn't even look. 55.27. So frustrating. Usually I'm having a brain problem today.